Oh, hello everyone. September 28th. All right, let's do this. All. Wait, what? All O1 data structure. Design a data structure to store the strings count with the ability to return the strings with a minimum and maximum counts. Implement the all1 class. Yeah, that's a typo. I don't know what this is. It's a typo. all1 initializes the object of the data structure. Increments the count of the string key by 1 if key does not exist in the structure. Insert with count 1. Decrement it. If the count is 0, remove it from the data structure. It's a guarantee that key exists in the data structure before the decrement. Get max key returns one with one of the keys with a maximum count. If no element exists, return empty. Get min key returns the one with the keys with the minimum count. If no element exists, return an empty string. Now that each function must run in O1 every time complexity. Damn. Okay, key consists of lowercase letters, guaranteed that for each call the deck key is existing at most 5 times 10 to the 4th. Alright. Do we have like a simple one? But simple one, you run the risk of this one not passing. Well, of course you have a map, right? You can increment, you can decrement. And then you need like because you need to return the max key and the min key. It's like a counter, right? This is a counter. You basically do a counter. I don't know what's the algorithm Python use for its counter, but my man, we can do. Holy crap! Ah, because we're changing the count. Yeah, it's like we have Dijkstra-ish, right? You keep the count of everything, and each time you get a new count, you push it into a priority queue, and then when you want to get a max key, you start popping. All right, you start popping until the one that matches. Okay, so it's not going to be O1, but we're gonna just do it first, and we're not gonna really make it work. Ugh. So we're just gonna do, damn it. We are just going to do a priority queue solution, which does not run in O1. We'll get it to work, but then we'll think about it. Okay, and then we'll need a priority queue. Holy crap, priority queue what? Exactly. Priority queue of what? It doesn't have. We need to create a node. Max queue. Actually, this will be a min queue. This is a max queue. Now I do a min queue. Okay, then don't need to do anything. Increment. This dot count. Put if absent key 0. Wait, hold on. That's not right. Put key get or default 0. All right, so here is what's interesting. Oh, my bad. We also need to say this dot max q dot add new pq element key, and this dot counter dot get key. Decrement. Well, we'll say if this dot counter, wait, so decrement 0 will be removed from the data structure. Okay, so if it's 0, we just don't even put in there, right? So if this dot counter dot get key larger than 0, min q. All right, so we're gonna go through max q dot. So wow, it's not empty. If peak wait, hold on, we're gonna do pq element top. All right, I say if top dot count is not equal to this dot counter dot get top dot key this dot max q dot pop poll. Alright, else they're equal, then we just return top dot key. And if going through nothing matches, we just return empty string. So basically we'll do the same stuff for this. So we just change it to min q. All right, let's make sure this one works, and then we'll deal with the other things later. Wow, this one doesn't work. What? Increment, increment. Increment, increment, and get max key, get min key. Oh, shoot. Yeah, my bad. We have to add to both. Same thing here. Yeah, max q need to add, min q need to add. Then get max. Yeah, I think the rest should be fine. Okay, I can say this is like a naive solution. Naive solution using priority queue to find the max, to find a key with max or min counts. The complexity of get max key and get min key can be, I don't know, what's the complexity? If you, on the same key, you keep changing, you keep changing, you keep changing. So it could be on, right? Where n is the number of calls made on the same key. This actually can time out. Let's try it. If the test case is good, then I'd expect this one to time out. Let's see if it times out. It should. If it doesn't time out, I will be surprised. Okay, the test case is pretty weak, and they just make it a little bit easy. This should not pass. But hey, we're passing, so I'm not complaining. But this is not what they're asking for. They're asking for is 01. This is not 01. I mean, is this 01? It's not. Unless we have some way to... I don't know. Is there any way? But even if we can avoid... Actually, it's not even on. It should be on log n, right? Yeah, that's not on. It's on log n. Because we also have the pole. So it should be on log n. My bad. It's actually on log n. So all we need is O1. How do you keep max and min O1? I think we have this discussion before. I forgot. I remember we have this discussion of is some easier way to keep the max. Count. So we have a key count, right? We can say K1 is some value, K2 is some value, K3 is some value. And then maybe we can create another but still you need to keep the maximum. So maybe is there a way with key is the count and the value is, let's say, K1, K2, K3, something like that. And if we can keep the keys, and then we have some method to keep the keys, keep the count sorted. But the thing is, the count, what can we do to keep the count sorted? And especially if some count is gone, then you need to go in there and then remove the count, which might change the order. Yeah, not really change the order. We need to redo it, or maybe I don't know. If we do a count, a priority queue of count. Okay, so we know the current count. Go in there to see. But if the count doesn't exist, we just remove. And what's the difference? Well, the difference is a key I have a count, right? If the key got incremented, I go to a previous count. Let's say this is a set. I go to the previous count, remove it. I go to the next count, add it. Okay, that's fine. I think these are all O1. Right? We can do all these are O1. And we have a new count. Then what? We enter into a priority queue. I mean, priority queue is not O1. Right? Priority queue is not O1. So we need some way, we need to keep track of the maximum. That should be priority queue. Right? It should be priority queue. Okay, we can take a look at the priority queue and we say if the current max Yeah, we still need priority queue, but we can no in the priority queue we say, but in the priority queue. And plus, if you use a set, how do you return a random one? I don't know. How do you return? I mean, if you find a count, you need to return a random key in this set. I am not sure if it's possible to return a random key in a set in O1. Do we have some hint? What's really a topic? Holy crap, doubly linked list. I didn't think about doubly linked list, really? How'd you do this double linked list? Huh. Doubly linked list. That's okay. I don't know. Maybe we say count is like a dummy node. A count will lead to no count. We can say is a dictionary and then lead to the node. So it's a k1, not a key one, and then key 2, right, and then key 3. We just keep adding, and if we want to remove, we can always return this. If some key gets removed because we're doubly linked, as long as I know the node, yeah, I can have a registry of the node. I can have the registry of the node, so it could be a string, key with a node, okay, string with a node. That is possible. Okay, but we still have, okay, so this doubly linked list can solve the problem of getting a key out of a set. Right, this is basically a set, so we can get a key out of the set. That is possible. And I can remove, yeah, I can remove, I can add, that's all possible. Okay, so now the question is, how do I keep track of the max or min? I feel like I've done this before, right? I feel like I've done this before. It's just, keep track of the max and the min. It has to be priority queue, isn't it? Like, what other method do we have to keep max and min? Tree map. Yeah, really? Yeah, it's gonna be log n. It's the largest key. Let's see. Tree map. Or maybe is that sorted map? No, sorted map is not. It's interface. Oh wait, hold on. No, it is. Oh wait, hold on. It is. It's sorted map. Yeah, we can use sorted map. Okay, so we have first key, last key, and when a count is gone, we just remove it. And we use you know, doubly-linked list to achieve this. Okay, I can see this one working, but it's still O1. I'm not sure what O1 can do. All right, doubly-linked list. Okay, how do we do? Frequency, node, next. Huh. Oh, wait. Wait, hold on. This is a double-linked list. It's not this one. It's a double-linked list with frequency itself. What? Map doesn't have key. Oh. Oh, I think I understand. Oh, I think what it means is the order is maintained by doubly-linked list. So I have a head, right? And I have a tail. If I add a new node in, that frequency is 1, right? Then we will create a frequency of 1. And inside this, I have another. So all the nodes recorded here, frequency is 1. Yeah, okay, frequency is 1. And then if I increment someone, frequency is 2. Right? So we have a map where we have a key pointing to the current node. Right? So when we give a key, we say increment. Right? We say increment a key. I go to the map to find its current node. Right? And the current node will tell you its frequency. Then if you add 1 and minus 1, add 1, you can add another node if it doesn't exist. If minus 1, you can go to the front, right? And then you add into that node, and then you need to remove from this node. Oh, makes sense, right? Okay, so we still have this question. How do we... we can return that one by its... Wait, hold on, no, we cannot. Like, minimum will be go from here to the first one, go inside, find a key, find one of the key in a set. But it's a set. How do we do that part? How do we get... I think I know increment, I know decrement. I hope I do. Iterator. That's how you do. Iterator. I did not know that. I did not know that it can be done this way. Iterator. Okay. Okay. Yep, I think I got what it means. So without reading the full implementation, I think I'm trying to implement it myself. Wow, this is smart. So I was asking, how do you keep track of the max and min? And the answer is you don't. You create a doubly linked list as a sorted frequency. Sorted frequency as doubly linked list. Okay? That's basically what it's trying to say. Sorted frequency as doubly linked list. And inside you keep, I mean, we are close, right? We have this frequency, and the frequency you have a set, right? That's we get that part. What we didn't get is how do you keep these keys sorted? And I was thinking, we can use sorted map, right? We can use priority queue, like all of these methods to do it. But then the solution says, no, we don't do all that. We use a doubly linked list to keep the order. Which now, in hindsight, it makes perfect sense. Right? It makes perfect sense because each time you increment something, you will be able to go in there, right? You can always go front or go back, and then you find it. And the min and max is always predefined. Doubly linked list to keep track of... I mean, this works, right? It works because we can always refer to the node. We always know which node is being referred to currently, right? And if you want increment, yeah, it's because you increment, you always go one. You either go previous or you go next, right? That's the key for double linked list to work. Which means when the number changes, it can only change by a unit of 1. But if we can be arbitrary, we can do this change arbitrarily, and this method doesn't work. right, quit the talking. Let's do this. I'm actually more in favor of it's comment out this code. I mean, it works. Oh, oopsie doozy. It works, but it's absolutely not the best solution. So we'll comment out. Yep, let's do it one more time. So we can say this time is doubly linked list node. I just call it node, right? Node. I call it count. I like to call it count. So we have count, and we need a set of string keys new hashtag. Okay. This is also something I did not realize you can use iterator to get something O1, right? And now we have node pre and node next. So when we create a node, we'll put key in it. Wait, hold on. Yeah, we'll create a node. Yeah, you create a node, you put a key in it. So string key. That's how I create a node. And really, you create a node, you put a key in it. No, I think you create a, you put a frequency in it. The count in it. That makes more sense. So this dot count equal to count. Okay, so this is using, let's just say, this solution uses the official solutions doubly linked list. The genius part is that we use the doubly linked list to keep the counts of all keys in sorted order. And this works because each time a frequency and a count changes, it only changes by 1 unit. In the doubly linked list, this means moving the key either to its current node's parent or descendant. The doubly linked, the min and max count value can be easily obtained by accessing the first and last node. Now this works for this problem. This works for this problem because the change to the count is restricted, right? Restricted to only 1 unit. If the change is can be an arbitrary value, the doubly linked list method will not work. Okay, so now what? Now we need a head and then we need a tail, right? And we need so we need a node, head, node, tail, and we need a map of string to node. Key to node. Okay, now we need to define them. This dot head equal to new node. Yeah, we're gonna put 0 in it. This dot tail equal to new node. Alright. And now we need to do something. We should say this dot head dot next equal to this dot tail. This dot tail dot pref equal to this dot head. And this dot key to this should be new hash map. Okay, so that's that. Now we need to do increment. All right, so increment, it depends. Yeah, it depends. So if this dot key to node dot contains key, right? So if it contains, then we can find this node, right? We find this node, and then we add. Well, it depends, right? It depends if the next node exists or the next node does not exist. So it will be something like this. Node current shall equal to, we can say node, right? Shall equal to this dot key to node dot get key. Right, so we get a key to the current node, and then we say if node, because we need to move next, so if node dot next is equal to this dot tail, so this is, we need to create a new node, right? Create a new node. Frequency, I can get the frequency from the previous one, so we shall say node, new node shall equal to node, new node, node dot count plus 1, so we're incrementing, right? And yeah, I see. So we need a private void delete node. Right? We need to delete, I just call it delete. Maybe we can say add as well. Okay, let's do delete first. So when delete this node, that's doubly linked, right? So we say node pre node dot pre, right? Node next node is node dot next. So to delete means previous node dot next equals to next node. Next node dot pref equal to previous node, and then node dot pref equals null. Node dot next equals null. That is to delete the current node, right? You have the previous node, you have the next node. The previous, the next come down, and the next pref come up, and then yourself. So that's delete. So the next one we say private void node add. Okay, add. Oh, add a new node. So add new node. So to add a new node, add a new node. Yeah, add. We need to add a new node. If we want to add a new node, and you give me the current node, so add new. Okay, don't say there's a current. So we need to add to right. Right, add right. So we add a node to the right of the current node, right? Okay, so how do we do this? We basically say again node next node, node on next node, right? And we need to add one, so we say new node. Oh, int count. It should be new node count, and then we need to add this add right. It's called current. Okay, now we say current dot next equals to new node. And new node dot previous equal to current. And new node dot next equal to next node. Next node dot previous equal to new node. And we'll return new node. This is the new one added. Okay, this is add. So we have add. Yeah, we always add to the right. So we just add and delete. Okay. So here, if node.next is equal to this dot tail, then we simply say node added node equal to add current and node dot count plus 1, right? We're incrementing. So the current, we have a node and we're incrementing, so we need to go to the next one, but the next one's already tail, so in that case we have to add a node, right? We have an add a node, so we say add a node equals the current one. We add a node with the current incrementing, right? So this is the next node. Now we need to do is we'll remove with and we'll add it. Hold on, I think there's an easier way. We say node added will be next node. Okay, and then next node. If this, we add a new node. Otherwise, like this. Else, next node equal to. Oh man, we could basically do this. Next node equal to node dot next is equal to this dot tail. If it is, we say add node dot count plus 1. If it's not, it's going to be node dot next. Right, this is the next node. So we get a next node, then we say node dot key. Wait, no. Node dot what? Shoot, I forgot. Node dot keys. We say node dot keys dot remove key. Next node dot keys dot add key. Right? That's it. Node cannot be resolved is not a field. Because this is this one. Right? There's a current node, there's the next node. We add or we get the next node, then we remove the key from the current node because incremented, and we add it to the next one. Done. That's good. All right. Then we say else. This is the key. Oh, wait a minute. This dot key to node dot put key next node. You need to change it, right? Else, if it does not contain, that's completely new. That's a completely new. That's actually not true. That's actually not true. So if it does not contain, if the key2 node does not contain the key, that means you will add it, that's the first one, right? Then you can say node will equal to this dot head this dot head, because both the head and tail both point to 0, right? And if which is just current node, right? Which is just current node. We don't node shall equal to this dot head dot next is equal to this dot tail. Yes. If it equals, we need to add this dot head 1. Right? If not, this dot head dot next. That's the current node. We don't have a next node. We just say node.keys dot add key. Done. Okay, I'm pretty sure we can do something very similar here. So we're gonna copy and paste here. All right. So what we have is okay. What we have. Oh my god! I think these are not. Hold on. There you go. So we're decrementing, right? If it contains, we get a node. And it's not next node. This is previous node. Shall be node dot previous is hold on. It will always have, right? It will always have. So what we're trying to do now is we go into previous, right? So we remove the current, we add it to the previous. That's all fine, unless the current is if you go previous, then we all need to remove the current node. It depends, right? It depends. It depends. What I mean by that is we always have we always have something in the previous, right? So I can always get the previous node. This is guaranteed, because if it contains, and it always contains, right? It will always contain. So I don't even need to do this check, and I don't even need to do all these, because it always contains. This is a requirement, right? So I can always get a current node. I get a previous node, right? I can get the previous node is just node.prev. Okay. Next is node.keys remove. Okay. And then if previous node.keys contains current key, then I say previous node.keys.add. Wait, no, we just add. Right, the current key, remove it, and then we add the previous. So we just say, no, this is actually not right. If previous node is not equal to this dot head, right, then previous keys dot add key. Right, if it's not the head. If it is the head, that simply means there's no more. The current key is no more, right? The current key is no more. Okay, so one more thing we need to do here is if node, if node.keys is empty. So current key can remove, right? If it become empty, then we need to delete it. It should not be there anymore. So if it's empty, then we need to do delete node. right? When you delete a node, if it does not exist anymore, or delete a node. So that's decrement, right? That's decrement. Of course, we also need to remove it from this dot key to node. Okay, so there's one more thing. How about we do it this way? You know, we handle it here. This is like all logic with node. And if it's not, else, if previous node is this dot head, which means the key completely decremented, then we say this dot key to node dot remove key. Okay, so node dot remove, so we do this, and if previous is not equal to this, I need to do hold on, I need to do this and this dot key to node dot put key previous node. All right, else we remove the key. Okay, that's decrement. Get max, basically we do tail the previous, right? So we say if this dot tail dot prev is equal to this dot head, return this as nothing. Otherwise, return this dot tail dot prev dot keys dot, this is new one, iterator dot next. This is a complete new one. Yeah. Use iterator to get any element from a set in O1 time. That's what I think, right? Get min will be exactly the same. Of course, this is going to be head.next tail, and then this is going to be head.next. Okay, so let's give this a shot. I did it very fast. We'll see if it works. No, it does not work. Which part? I have increment, get max, get min. We got all of this. Increment again, get max. So we have an increment of lead. So hold on, increment of get max, get min. Increment of get max, get min. Increment, this one is lead. Get max is hello. Hello. So get max has some issues. Okay. Where do you think we got it wrong? Where do we think we got it wrong? Oh shoot! I forgot to feed the cat. Alright, need to feed the cat. Damn. increment. I think I know where I got it wrong. Because when you increment, something can be empty as well. Yeah, when you increment hello twice, the node attached to count of 1 become empty, and that one should be removed. Yep. That was at least one of the bug, one error. Alright, come on. Alright. So I think the problem is here. Increment. So if it does not contain a key, we always have to add it. Okay, that is fine. But if we contain a key, we have a node. We have the next node. Nodes.keys here. This is the problem. Because nodes.keys.remove. Yeah, we need to say if node.keys is empty, delete node. Okay, let's try. So we add this piece of logic. Madre mia. We add this piece of logic, it's still not right. Huh. Wow. That was powerful.
I'm scared of the cat.
Oh, wow.
Jimbo buried himself under the bed sheet.
Oh, I need to make the bed. Alright, there are a lot more things to do. But this one right now is not working. Alright, I need to make the bed. I'll be upstairs. Alright, cats are fed. I think I figured out what went wrong. What went wrong is this add. Yeah, because now we can remove node when we are incrementing, right? Which means when we add a node, I'm gonna do it again. When we're incrementing, we can add. When we're decrementing, we can add as well. That's the thing. When incrementing, decrementing can add in both ways. And of course, it doesn't really make any sense in this case, but this definitely is something wrong. Okay, let me go through this one more time. Okay, one more time. We're incrementing, right? So we get its current node, and we try to find the next node. Okay, so we say if next equals the tail, so which means there's no next node, so we need to add a node with this new value basically to the right of the current node. Alright, otherwise if it's not a tail, then we have a node, so we get this next node. In the current node, we need to remove the key, and if we have no more keys, then this node gets deleted. And the next node's key will add the current key, and we'll set this. I feel like this makes sense. And if the key to node does not contain a key, so we'll always put into 1, then we'll add again, right? Then we'll add a new node with count as 1. Makes sense. Or we use head.next. This is also not right. This is also not right. Oh my god. There is a lot of issues here. Yeah. Yep. Right? It's head.next.count if the count is not equal to 1. Then we need to add 1. It doesn't really matter, right? Otherwise, I use the next. And node.keys.add and this key to node.put key. No, I don't know why I forgot to add this one. Alright, this is important. And when you say add, it depends. Yeah, this one depends. Because if the count is larger than current, we add to the right. If it's smaller, we add to the left. Right? We get the next one. Else previous node. Then previous node dot next equal to new node. Current dot pre new node, and a new node Yep. Yeah, okay. Decrement. We can always get it. And we always, because decrements always go previously. So we say pre-node, we check it. Node of previous, yes. And we remove it. If it becomes empty, we remove the node. If the previous node is not equal to head, then we'll add to it, right? Yeah, this is also, hold on. If previous node is not equal to head, that's not true, okay? That's not true. So we get a previous node, yes. Ooh. Okay, hold on. We get a current node, right? And we need to minus 1. So we check the previous node. Okay? That's fine. We can say here, if node dot previous node dot count is equal to node dot count minus 1, right? If it's equal, then I can move there, right? If it's equal, I can move there. I can say node dot previous dot count, node dot previous dot, oh, it depends if it's 0. Okay, if node dot previous is equal to this dot head, shall be not equal to this dot head. Right, if it's not equal to this dot head, I say node dot previous dot keys dot add key, and then this dot key to node dot put key node dot previous, right? If node dot previous is equal to head, then we just let it delete, right? We just let it delete, right? That's basically what it is. We just let this current got deleted, which we also need to do, which is here else, right? If node dot pre is equal to head, then we shall say this dot key to node dot remove key, right? We shall remove it. This is when the count, right, is equal to node dot count minus 1. Now, if the previous count is not equal to node dot count minus 1, then we need to create a new node, right? Then we need to say node dot, now we need to say add node dot count minus 1, right? We say node, new node, so you go to this, right? This is the new node. Then what? Then we need to say, we add this new node. We add this new node to it. New node dot keys dot add key, right? Because we add this new node, with this frequency, we add this to it. This dot key to node dot put key. Yeah, we're gonna call it previous node. I don't like new node. Let's just call it previous node. Alright, so previous node and then this. Okay. That looks pretty good. And we're gonna delete all this. Then node dot keys dot remove key. If node dot keys is empty, delete node. I'm gonna think about this. If we have some, right? If we have some, then oh shoot, and this is the same. Damn it. Oh. If, oh my god. Yeah, it's the same thing. If node.next.count is equal to node.count plus 1, right? If it's equal to, so the next node is equal to, then I can simply say I can simply say node.next.keys.add key. This dot key to node.put key node.next. Done. Else node next node shall you go to add node dot count plus 1, because the next one is not equal to, right? So we add a new node. Once we add a new node, next node dot keys dot add, oh my god, key, right? We add a current key to it, and after that this dot key to node dot add, not dot add, dot put key next node. Then nodes remove if this, delete these two. So now they're about the same. I don't think this is necessary. No, this is necessary because we have to consider if it contains key. So we have the current node, and then from there we start to work on it, right? We say if the next one is, then we do it. If the next one is not, we have to create a new one, and then, you know, and now we do this. Now this is, the current doesn't contain, so you're 1. So you have to check for 1, right? You check for 1. And you will add it 1. Yeah. Now these two are exactly the same. I think it is the same. Node next node shall equal to node.next.count equal to node.count plus 1. If it's equal, node.next. If it's not equal, add node dot count plus 1, right? That's exactly the same. And then these two lines are the same. Right? Are the same. Node on next. I mean, we don't call it node on next. We call it next node. Right? The next node, we say if the next one is plus 1, then we move there. If the next one is not, we add a node. And then the next node, we handle this the add key, update it, and if current node remove and becomes empty, we delete it. Otherwise, yeah. So here, but here is different, because if the previous node is equal to, I'll move to the previous, right? I basically move to previous. Otherwise, I need to add one. And then based on what the previous is, I can do something similar. I say node previous node shall equal to node.previous.count is equal to node.count minus 1. If it is node.previous, if it's not, we add node.count minus 1. Right? This is exactly the same logic. Exactly the same logic. Right? It's the same logic. But what's different is if the previous node add key. So if previous node is equal to this head, right? Then this key to node remove key. Else, if it's not, then previous node keys add key, and this key to node put key previous node, and then all of this can be deleted. Right? So now we kind of combine the two. We get a node, we get the next node or previous node, and then we add the next node, which I guess we add a previous node. We set this, and then we check node, and we delete node. But we have one more, which is have to do this. Okay. So now with this, I don't even know how many iterations we have gone through this, but it is a great problem. Really, it can really screw you up on the logic. This is one of those logic that I don't think it's difficult, but it's very complex. It's a really complex logic, and I might still get it wrong now. No, you get it right. Ooh-wee. This take a while. This take a while, but no, you take a while. You do get it right. You certainly can get it right. Great problem. Absolutely great problem. Absolutely great problem. All right, that's it. We solved it, and we did not see the detailed implementation, but I know it's complex. Right, it's very complex. But what we did do is we use priority queue as our first naive solution, and then we kind of understood how the official solution uses doubly-linked list to keep the count in sorted order, and there's a lot of logic involved how to make increment and decrement work, but overall it works. Okay, that will be it. I will see you guys tomorrow. Adios.